Chapter 10, Fluids, Part 1. First, I'd like to talk with you about density. And for density, we're going to use the symbol, a Greek letter rho, for density. Now, density is equal to mass divided by volume, where your mass is in kilograms and your volume is in cubic meters, and that's going to be our SI unit for density. Another term similar to density is called specific gravity, and specific gravity is equal to the density of whatever substance you're looking at divided by the density of water, so that the density units end up canceling. So let's say you have the density of air, which is 1.29 kilograms per meters cubed, and you are asked to find the specific gravity of air. So the specific gravity of air would be the density of air divided by the density of water, which would be 1.29 kilograms per cubic meter divided by 1,000 kilograms per cubic meter. And notice that the kilograms per cubic meter do cancel, and I'm left with a specific gravity of air of 1.29 times 10 to the minus 3. And that's the specific gravity of air is equal to that value. Notice no unit. Okay, now I'd like to define pressure. In general, pressure is equal to the force applied to an object divided by the area upon which that force is applied. And the SI unit for pressure is a Newton per meter squared. Let's do an example. So we have a mass of a person, they have a mass of 60 kilograms. And what is the pressure this person applies on the ground? Let's draw a free body diagram on what the person does on the ground. So the person has a weight down. And we know that pressure is equal to force over area. In this case, the pressure that the person is applying on the ground, the force that this person is applying on the ground is this person's weight, divided by the area of the person's feet. So if for 1 foot there is an area of, let's say, 250 square centimeters, since this person has 2 feet, there will be an area of 500 square centimeters. We do need to convert this value of square centimeters to square meters, so I wanted to go ahead and show you how to do that. So we have 500 square centimeters, put that over 1, and I need to convert the centimeters to meters, so I'm going to put centimeter in the bottom, meter in the top, and I'm going to do it again, centimeters in the bottom, meters in the top. There are 100 centimeters in a meter, 100 centimeters in a meter, and if you see here, the centimeters cancel in the bottom with the square at the top. The other centimeter in the bottom cancels out the other centimeter. So I am left with a unit of meter squared, which is what I want. And then multiplying across, I get, and multiplying the bottom, and then dividing, I get 0.05 meters squared. So that is the area that the person applies to the ground. So the pressure then, which is going to be the mass of the person, 60 kilograms, multiplied by the acceleration due to gravity, 9.8 meters per second squared, divided by the area of 0.05 square meters, and I get an answer of 12 times 10 to the 3 newtons per square meter. Now, more about pressure. One of the things we know with pressure in fluids is that pressure increases with depth. So we have a new formula to look at, and that is the pressure is equal to the density of whatever fluid you're dealing with multiplied by the acceleration due to gravity multiplied by the depth. Another way of looking at this is your change in pressure is equal to the density of the fluid multiplied by the acceleration due to gravity multiplied by your change in height or change in depth. Here's an example. We have some water tower up on a hill, and we have some sort of conduit for the water to travel through. It goes down the hill, underground, comes up into the house. And the question is, what is the difference in pressure between where the water level in the water tower and where the water comes into the house? So what is that change in pressure? And one of the first things we need to do is figure out, well, what is the change in depth? So the highest point of the water is right here, and the water goes into the house at this point. So my delta H then, my change in depth, is right here. So what is the pressure where the water goes into the house? Or what is the change in pressure between the top of the water level in the water tower to where the water goes into the house? And so the formula we're going to use for that is rho g delta H. Let's go ahead and say that our delta H value, let's give that a value of 30 meters. Maybe we could fit that in here, 30 meters. And just plugging into the equation, the density of water is 1,000 kilograms per cubic meter. G is 9.8 meters per second squared, and delta H being 30 meters. And plugging that in to the calculator, I get an answer of 2.9 times 10 to the 5 newtons per square meter. Now, a newton per square meter is also called a Pascal. So we can also write this as 2.9 times 10 to the 5 pascals. And so that is our answer there. Alrighty, now I'd like to talk with you about atmospheric pressure and gauge pressure. Atmospheric pressure, I'm going to give a subscript of ATM, P to the sub ATM, and for gauge pressure, P to the sub capital G. Now, 1 atmosphere of pressure is equal to 1.013 times 10 to the 5 newtons per square meter, or pascals, and that's equal to 101.3 kilopascals. Now, gauge pressure, or P sub G, is equal, like you were measuring the pressure in a tire. That's the pressure above and beyond atmospheric pressure. So if we wanted to find something called absolute pressure, what I call P to the ABS, that's equal to, you also have to consider your atmospheric pressure plus your gauge pressure to find the total or absolute pressure. Alrighty, let's talk about Pascal's principle. Pascal's principle is very simple, and that is the pressure out of a system is equal to the pressure in. Let's talk about an example. Let's say we have some sort of system to lift a car. We're at some sort of mechanics, and they need this way of lifting a car lift, and they're going to use Pascal's principle in order to easily lift a car up, because a car, of course, weighs a lot. And so we have some sort of piston face on the left side, and we want to apply a force on this piston face. We'll say that's the force in, or F sub I, and on the other side of the system, because it's all connected by some sort of fluid, let's say, or gas, if it's a fluid, we'll call that a hydraulic system. And if we press fluid in on the left side, then there will be some sort of force out on the right side pressing upward on the car. Now, I know because of Pascal's principle that the pressure out is equal to the pressure in, or I could say the force out over the area out is equal to the force in over the area in. And let's say we wanted to find out what is the force required in. Let's find out what that is so we can lift this car. So what we can do is rearrange this formula for the force in, and that's equal to the force out multiplied by the area in over the area out. Now these piston faces, going back up to the diagram, these are circular. So the area of these circles is pi r squared. So let's write this out again. This will be force out. The area in is just pi r, the radius in squared, over the area out, or pi r, the radius out squared. If you look closely here, you can see that the pi's cancel, and so I'm left with the expression of the force in is equal to the force out multiplied by r sub I squared over r sub O squared. So let's take a look at this. The circular area that the car is on, if we can increase that, that's what I call the radius out, then it will decrease the force that I'm required to put in to raise up that car. Measurement of pressure, gauges, and the barometer. The barometer, or sometimes referred to as the U-tube, is used to measure pressure. So on the right side of this U-tube, there's pressure being measured. And what ends up happening is you have some sort of differential in height of a liquid inside the U-tube or the barometer. So this liquid pushes up more on the left side, and because we know pressure increases with depth, all we need to do is measure this difference in height from the left side of the tube to the right side of the tube, and we get a delta H value. And we can use that delta H value by saying, oh yes, the gauge pressure, hang on one second here, the gauge pressure, or P sub G, is equal to rho G delta H. And then once we know what the gauge pressure is, we can then find the total, or absolute pressure, by taking the atmospheric pressure plus the gauge pressure. The only other thing we need to make sure we're careful of is the density of the fluid. So just pointing this out, this rho here, this Greek letter rho, is the density of the fluid. And typically in barometers or U-tubes, you may have alcohol as a fluid or mercury as a fluid. So you need to make sure you know what the fluid is so that you put the proper density value into the formula. Lastly, I want to talk with you about something called buoyancy or buoyant force and Archimedes Principle. Now, Archimedes Principle has to do with something called a buoyant force, or F sub B, and it's equal to the mass of a fluid displaced by an object submerged in fluid multiplied by the acceleration due to gravity. Let me give you an example to explain what this is all about. There's a very famous story about Archimedes, and he was asked to determine the density of the object. He was asked by a king to determine if a crown that was a gift to the king was actually solid gold or just gold leaf on the outside of the crown. So Archimedes found a way to determine the density of the object. And what he did is first he took the object and he weighed the object with a typical scale. And so I have this picture here, and drawing a free body diagram on this object, we can see that we will have a mass of an object down multiplied by the force of tension, not multiplied, but upward force of tension up on this object. I'm going to call this scenario 1, so I'm going to call this the force of tension sub 1 acting on this object. Then what Archimedes did is he took this object and submerged it in a liquid, and I believe it was water. And so let me draw that out for you. So now Archimedes submerged this object in water, and now he has a new free body diagram. We still have the mass of the object downward, We still have a force of tension upward, but it's different than in the first case, so we're going to call it F sub T2. Let's call this situation 2, by the way. We'll call this situation 2. And there's another force, though, because the object is submerged in water. And that other force is called the buoyant force, or F sub B. So the problem to solve here is to find the density of the object. And we know the density of the object is the mass of the object divided by the volume of the object. So to solve this problem, we're going to look at three things. First thing we're going to look at or refer to is Archimedes Principle, that the buoyant force acting upward on an object is equal to m sub Fg. We're also going to look at density is equal to mass over volume. And we're also going to use Newton's second law of motion. In case 1, using Newton's second law of motion, the force of tension upward minus the weight of the object downward is equal to 0 because the object is stationary. Or the force of tension in case 1 is equal to the mass of the object times g. Or the mass of the object is equal to the force of tension from object 1 divided by the acceleration due to gravity. Keep in mind that this force of tension value in case 1 is given on a spring scale, so that value can be given. So just in case 2, the force of tension for the second object upward plus the upward buoyant force minus the weight of the object is equal to 0. Rewriting this equation, I can say the force of tension from the second object plus m sub Fg, that's the equation for buoyant force, minus the force of tension in the first case is equal to 0. Now remembering that density is equal to mass over volume, the density of the fluid is the mass of the fluid divided by volume of the fluid, we can rewrite this expression as the mass of the fluid is equal to the density of the fluid times the volume of the fluid. And we're going to substitute this expression in for mass of the fluid. So let's rewrite the expression for substituting in density of the fluid times volume of the fluid for mass of the fluid. Lastly, we also need to realize if an object is fully submerged, the volume of the fluid displaced is equal to the volume of the object itself. So we're going to substitute in volume of the object for volume of the fluid displaced. And rewriting this again, I get force of tension of the second object plus volume of the fluid, which would be volume of water, multiplied by the volume of the object times g minus the force of tension in the first case. Looking at this equation, we only have one unknown, and that is the volume of the object. So what we're going to do is rearrange this formula for volume of the object, and here it is. So here's the equation for volume of the object. And if we're going to find density of the object, we just need the mass of the object divided by volume of the object. The mass of the object is the force of tension in case 1 divided by the acceleration due to gravity. The volume of the object is written above. Should we write that? And rearranging this equation, I get the density of the object is. So here's an expression for the density of the object. We have the force of tension in the first case, which is the reading on the spring scale in the first case, multiplied by the density of the fluid, which is the density of water, divided by the quantity of the force of tension in the first case, which is the reading on the spring scale in the first case, minus the reading on the spring scale in the second case. Alrighty, practice problems, page 281, 5 and 11, and page 282, 17 and 27. And the answers are in the back of your book. Good luck. By the way, this is due our next class meeting, and good luck.